generation. I am the presenting author, Lucheng Chao from Chongqing University, and I'm also the first author of this paper. We are going to divide our talk into 5 sections. The first section is motivation, and the stochastic generation of the large language model. Second is my model, which is a shared context branching model with a prefix partition analysis model. The third one is LinguaLens, our major system, with 2 coordinated fidelity-aware views. The fourth one is an evaluation with a 960 generation corpus, 2 case studies, and an expert walkthrough. After that, we have a conclusion of my major contributions and takeaways. First of all, the motivation of my work. We all know that large language models generate text stochastically. Even if you input the same prompt, the same decoding parameters, they can yield very different outputs on each round. But how can we evaluate repeated generations to evaluate them actually diverge, or does it matter? So we are going to say that the same prompt, the same model 8 rounds, you have 8 different outputs. When you have to evaluate the differences between them, aggregate reliability scores, flatten this. Reading one output at a time cannot cover it. Different people have different views about the question. Because, for example, for a prompt engineer, he may ask that, is this wording stable across rounds? For an auditor, he may care about, does this high-risk answer reproduce? For a linguist, he may want to know that when and how does machine-generated variation appear. So we have done a lot of research during this time of our work. So I identified the gap in the existing tools. All tools in fact measure on the model internals such as attention, neurons, or embeddings, or treat each generation as a single artifact. So the question remains open: which uncertainty token positions actually produce different outputs across rounds? So based on this finding, we have identified very interesting finding that model uncertainty does not always mean rebranching. Even high entropy, they don't always mean rebranching. Model uncertainty and realized instabilities are only weakly related. We have identified two instances. One is high entropy but stable instances, and another one is low entropy but branching points. We have to design a system to identify these 2 instances based on the information we have known. So we designed a design study with 6 computational linguists and the natural language processing researchers, and designed 3 tasks based on them. The first task is to diagnose token level instability. The second task is to assess structural consequences. The third is to explore cohort divergence. Based on these 3 tasks, we have designed 3 design requirements. The first design requirement is to show the 4 distributional shapes, such as top K, KMS. They are directly from the model. We have got this model, then we got this information. And not just as the chosen tokens for probability. After that, we have to align distributional uncertainty with branching indicators at each position. As last one, but not least, restrict branching its comparison to prefix valid positions where alignment is actually meaningful. Pay attention to this prefix valid positions, because this shared context branching model, we can actually compare between different rounds. For example, you have 8 rounds here. On the top right, it's a shared context partition tree. The partition tree starts with 4 the same token in the beginning. Then it's split into British, with 7 chooses British, and another one chooses the. And we drop this, and we continue to trace the tokens after the British one. Then we get because, for, and as. And we drop this minority. and we also focus on the majority. And during this process, token by token, we get this partition tree. This is an actual model of it, but if you have to focus on how to understand it, on the right is an illustration. Now we know what is a model is like, so we're going to design a system. It's called a LinguaLens, a visual analytic system with complementary modalities we'll use for branch detection. This is my system overview with 2 coordinated primary views and some supporting linguistic context. At the top right is the token decision landscape. This is a compact visual channels which illustrates the token decisions on each token. For example, if I click on it, it shows the major path, which means previously I followed the major path. I click on it, and it shows the probability of each token as the word chosen by this model. And after that, we have a branching explorer, which shows the 4 parameters we have to have in the model. They are actually ran from the model itself. It is major path. It shows the 4 view of it. And this is a branching explorer. It lists all the branching points of it, and this lists every token we have in the model. And this panel is an alternative panel which shows the alternative token positions we have from this model. And on the bottom, we have linguistic contexts that are supported but not major. How am I going to introduce our first view of token decision landscape? It consists of 3 different visual channels. First one is fixed baseline. They are also the same Tor. And I'm going to say that if I click on it, I see that the probability of this token is very low. And this is a branching point, it says. And the second one is a margin line and entropy. The margin line is a red line here. And the top 1 probability minus the top 2 probability. So if I'm going to identify from this point, you can tell that if the margin line is very low at some point, it's more likely to produce real branching. And after that, we have a coverage band. It shows the major cost. How many active rounds we have to this token. So we are going to say that if you are looking at 35 as this token, it drops a little bit to maybe a half, which means that we have to handle to the second part, second view, which is shared context explorer with 4 coordinated subviews over the complete partition tree. So it shows the 4 tree of the couple flow. We have identified some branch timeline during this. And this is a cross-rank alignment. We actually list every token for analysis to make some analysis. After that, we have a branch detail, which shows alternative tokens. So we do an evaluation based on the system. 960 generation corpus analysis. We have found that GPT-4 tend to have more branching points than GPT-4 mini, which is a very interesting finding. And after that, the O entropy branches also rises with a sampling temperature T. So this is very interesting that entropy branch correlation stays very weak. This is a very interesting finding. So after that, we have 2 case studies and a formatic formative expert walkthrough. The case one is to screen, then confirm. In this case, the analyst first scan in the TDL, then escalate to the explorer to confirm branch point position 7. This is a normal case. In the case 2, it's a little bit different now. When you input with this input prompt, extend entropy in information theory with model TD for meaning, we found that runs diverge immediately. So we have an empty shared prefix, which means the analysis lives entirely in the explorer. So the only there's a view 2 takes place here. So we have a formative expert walkthrough with 4 domain experts. The expert from the system to verify token level instability and its downstream consequences. So for a conclusion, we have 3 contributions here. The first contribution is a formalization. We have a shared context branching, prefix partition model with coverage and survival metrics. The second and the third one is our views with 4 coordinated subviews with 4 partition tree. The third one is token decision landscape is another view, which shows the distributional screening with diagnostic channels and operating analysis. So in a word, LinguaLens shows where your model branches. It's a very interesting moving analysis from aggregate signals to token level divergence exploration. So thank you for your listening.